Hi, welcome to video 4 in my series on Introduction to Data Science with R. Uh, Today, we're going to be talking about exploratory modeling, and the reason why we're finally getting to this point is that we've done enough data analyses to warrant some additional intuition, some additional reinforcement for the things that we may have gleaned from the data. And I know that there's probably been, well, I shouldn't say I know, I'm willing to bet that there's been a non-trivial contingent of folks that have been watching these videos going, man, I'm 3 hours in and we haven't done anything that I thought even remotely resembled what data science would look like. That is building models. And at the risk of sounding preachy, I've talked about this before, but I'll mention again, 60 to 80% of the time spent on a data mining / data science project is relatively low-level work of getting data, cleaning data, massaging data, validating data, confirming what things mean with subject matter experts in the business or what have you. And very little of it is modeling. Not to be too cheeky, but you can really think of the modeling aspect as the tip of the iceberg, pun intended. Given that we're looking at Titanic data, of the whole data science lifecycle. That being said, exploratory modeling, in my opinion, is actually something that's quite beneficial, and this is something I wanted to go through with you today, given the place where we are at in the life cycle. So let's start with the intuition of why you may want to do some exploratory modeling. So first and foremost, there are many machine learning algorithms that can go through the data as they're being trained and can look at the variables, the features, the columns, if you will, in the data, and actually decide which of these variables are important in terms of being predictive and those that are not. This is typically known as feature selection. And some models do this explicitly. For example, if you're using a logistic regression algorithm that implements what's known as L2 regularization, if you don't know what that is, it's fine, doesn't matter. L2 is an explicit way of doing feature selection, and some algorithms do it implicitly. So for example, as we'll see, random forests do this as part of the algorithm of repeatedly training decision trees. Each individual decision tree will pick and choose which variables, which features are beneficial for understanding how to predict the data. And then over the course of many trees that are being trained as part of a random forest, you kind of get this emerging idea of what variables tend to be important and which ones don't. So this is great, right? Because it can validate some of the stuff that some of the intuition that we've gleaned from looking at the data, which is this whole idea of women and children first, and that wealthier folks rather than poor folks tended to survive. So we can use this exploratory modeling technique to validate some of the things that we've gleaned from analyzing the data. So, and I kind of just jumped into the second bullet point here, which is there are a number of scenarios where this idea of number one can be helpful. First and foremost is in scenarios with lots of features, that is what's commonly referred to as high-dimensional data, exploratory modeling can assist us in identifying high-value candidate features first. And this can be important. Imagine, if you will, that you've got a data set with 300, 400, 500 variables, features, columns. It may be beneficial because your time is valuable as a data scientist to start, whittling that down a little bit and saying, look, before I analyze each one of these pieces of data or each column, each feature in detail, maybe I should target some of the stuff that has more likelihood of being predictive. So exploratory modeling can help you with that. Now, unlike in this video series, you can start with exploratory modeling in the beginning, but since our data set was small, it only has 10 features. It was I wouldn't do that normally. I would start the way we have in this video series. Okay, this second bullet point is where we're at in the video series, which is we've done some data analysis and we want to use exploratory modeling to provide additional insight or confirmation of what we've gleaned from the data. And we'll see this later in the video series when we actually do some feature engineering. Can we validate that our feature engineering is useful? Now, in our case, we actually have done a small bit of feature engineering already. So the title feature that we created as a proxy for both the gender as well as the age of a passenger in the Titanic is an example of feature engineering. Another one that we'll see in the video today is family size is also a feature that we engineered. But so we'll confirm this. So really, I guess we're combining both of these things in today's video. Okay, now here's some characteristics that you want in your exploratory modeling, right? It needs to be simple, fast, and effective. Let's talk a little bit about that. So it needs to be simple. So models have these things called hyperparameters. And we'll see this later in the video when we take a look at the random forest algorithm. But in terms of our programming, literally it's a function call, and this denotes the number of parameters that you can tweak. And the way to think about it is the hyperparameters are knobs and dials. They're ways of tuning in, dialing in the performance of the tuning, the training of the algorithm to fit the particulars of the data that you have in your training set. And some algorithms, for example, like deep neural networks, have tremendous numbers of hyperparameters that you have to worry about, and their performance, their effectiveness as models varies widely based on how you set those. And that can be a non-trivial endeavor. So generally speaking, when you're just doing exploratory modeling, you don't want to do that because it takes too much time. Another thing that we want to worry about is data pre-processing. For example, do I have to convert factor variables, categorical variables in R to numeric variables, essentially a set of binary ones and zeros instead, because the algorithm that I'm using only works with numeric data. It does not work with factor or categorical data. So generally speaking, while this isn't that big of a deal, later on we'll probably take a look at how to use the caret package to do this for us. Pretty easy. It's just extra work. So if you can avoid it, it's probably a good thing. Very intuitively, we want our exploratory modeling to be fast. We want to pick algorithms that train as fast as possible. So for example, logistic regression is a classification algorithm that you could use for the Titanic competition, and it trains, generally speaking, very, very, very fast. So that's a good benchmark to say, look, am I as fast as logistic regression? Great, that's pretty fast. And lastly, we want our models to be effective. And this is where, for example, a logistic regression is very fast, but out of the box, it's not necessarily particularly effective because it is at base a linear model. And as we've seen in our data analysis of the Titanic data set, which is actually quite typical in my experience for business data in general as well, this is a very non-linear problem. So this boils to this last bullet point that I've highlighted, which is we want our models to be effective. So we want our exploratory models to be powerful enough to work with the data that we have at hand so that we can put stock in the results that it gives us. And in the case of Titanic, this is a very complicated data set. It's highly nonlinear because we've seen that, well, if you're a master if your title is master and you're in first class, you basically survived. But if your title is master and you're third class, well, you survived, but we don't really know why necessarily yet, based on the data that we've analyzed, why that would be the case. It may just be purely random for any number of reasons. So you want things to be effective. And the whole idea is when you take these things in aggregate, this is really this idea of cycle time. How many iterations of a model can I crank out in a given hour of activity? Because as a data scientist, my time is valuable, your time is valuable. So the more iterations we can crank out in a unit of time, the more value we can generate, because we can try different scenarios and explore and create experiments and that sort of thing. So we want our exploratory modeling to be fast, simple, and effective. Okay, so that leads us to arguably the king of exploratory models, in my opinion, which is the random forest algorithm. Now, in this video series, we're not going to go in depth on any particular algorithm that we're going to use, mainly because, quite frankly, there are better resources available on YouTube or on the internet than I could provide, so why reinvent the wheel? So I'm going to provide in just a bit some great resources for learning random forests off of YouTube. We'll see that in a second. So don't worry if you don't understand what a random forest is. I'll give you some materials to learn that. What we want to emphasize for this video is that random forests meet all of the intuitive criteria that we talked about above. So first and foremost, as I mentioned earlier, they do provide feature selection automatically. It's arguably implicit, but random forests do it, which is great. They're extremely simple from a development perspective. They're arguably ridiculously easy to use in R out of the box because the default hyperparameter values work very well. So you can actually get quite a bit of value of just passing in your data and your training data and your labels, and you can just tell the random forest to run, and you can actually just look at it, at the results, and it's actually quite valuable with just that simple line of code. Now, random forests are also really awesome because they can handle numeric, categorical, and correlated variables without pre-processing. So for those of you who aren't familiar with correlation, basically it says, look, if I've got two numeric variables, let's say, and they both tend to have high values at the same time, and they both tend to have low values at the same time on a row by row basis, that means they're highly correlated. In many machine learning algorithms, especially linear algorithms, tend to have a problem when you present correlated variables to them. So often what needs to happen is you have to do some pre-processing. Let's say you use something like logistic regression. You don't want to put two highly correlated variables. You don't want to present two highly correlated numeric variables to a logistic regression algorithm when you train it. So you have to worry about that. But random forests actually handle that pretty well, so you don't really have to do much, which is great, right? It just lowers that bar for doing some high volume iterations on our exploratory modeling. So random forests are relatively quick. They're not nearly as fast as logistic regression. I mean, logistic regression just blows it out of the water, to be quite frank. But when you compare it to other potential exploratory algorithms that have all of the other benefits that random forests provide from the data scientist's perspective, it's way faster. For example, any sort of multi-layer neural network with multiple hidden units, aka deep learning, it's going to blow it out of the water in terms of training time. SVMs, support vector machines, same deal. It's going to be much faster than that. And random forests will tend to be faster as your data set grows than those other options. The amount of time, the increasing amount of time it takes to train a random forest won't grow nearly as fast as those other options that I talked about. Now, random forests are effective. So when I first started Kaggling, so 2-3 years ago, random forests were essentially the gold standard. Almost everybody used them. There were many teams that won Kaggle competitions using only random forests. That's since changed with the advent of deep neural networks and boosted tree packages like XGBoost. Random forests are still a go-to algorithm, and they're definitely part of any winning team's ensemble. So they're still very powerful. They've been eclipsed by some more recent technology. We will use XGBoost later in this series, for example, instead of a random forest for our submissions to Kaggle. But random forests are still a go-to algorithm, and you should not feel like you're shorting yourself at all if you use them in your work. So great, random forests, awesome. Okay. So let's go take some look at some resources on YouTube. So finding some stuff on random forests is really easy. So just go to YouTube, just type in random forest Kaggle as your search criteria. And what I recommend is about third here on this list, random forest tutorial from Kaggle. It's 3 videos. Okay, so let me pause that. Okay, so this is a really great video. I would recommend watching all of it. It's from a while back, but it's really talks about how you, it's really focused on competing in Kaggle competitions, which, as you know, I heartily recommend to everybody to do, all the people I mentor. It's a great way to build your chops. And this video really talks about, getting prepared for doing data science competitions on Kaggle. But in general, it's equally applicable for anything that you do in your professional life as a data scientist. Now, the Random forest specific stuff, if you don't want to watch the entire video, starts around 40 minutes or so. And so this is some code that he wrote for his own random forest implementation. But you can watch this video, and it gives you a really high-level introduction to random forests. Now, this video here is actually a lecture from the University of British Columbia, and it's actually very in-depth. If you search on this lecturer's name by Nando D. Freitas, hopefully I didn't butcher that too badly, he also has a really good video talking about decision trees. So a random forest essentially is a collection of individual decision trees. So you can watch both of these. And I know that if you watch all three of these videos I just recommended, you're looking at 3-4 hours worth of material, but it's goodness. So I would highly recommend it if you can, if you've got the time to do it. Okay. That being said, let's go ahead and plop into R here. I'll maximize this. So what I'm going to do is I'm just going to run all of the code from the series up through the end of video 3. And as usual, we're going to see a bunch of output here and a bunch of diagrams, plots pop up. Now you'll notice that I'm going to start adding these blocks into the code. I'm noticing it's starting to get long. So starting from now on, you'll see blocks that'll show you in the file on GitHub, hey, this is where we're at for video 4, video 3, so on and so forth. So hopefully that'll be a little bit helpful. Okay, there we go. So first thing that we want to do is, if you've got a relatively clean R installation, an RStudio installation, you probably don't have random forest. So let's install it. So click the Packages tab over here and then click Install. And just type in random forest. Now we just want the plain old random forest. Now, as you may have noticed, random forests are popular and there are many variations on it, but for our purposes we're just going to use the de facto random forest implementation here. Okay, so if you say that, let's just go ahead and restart the R session here. Okay, so everything's installed. We can go ahead and load it. Now, as always, don't be afraid to use the help system. So the function in question is oddly enough just called, or not oddly enough, called random forest. So we can just go ahead and execute the help function on that. And let me expand this so you can see a little bit better. Okay, so here's the function definition in R terms, right? As I said earlier, all of these are essentially hyperparameters for tuning it. Great news is you don't need to worry about any of that for right now. You can explore these in depth if you want to over time. I know I have, as I've competed in Kaggle competitions, but the good news is for our exploratory efforts, we really don't need to worry about too much. Okay, so let's start going through the code. First thing we want to do is let's take a look at exploring just P-class and title. As you saw ad nauseum in previous videos, P-class and title were really basically the pivot, the drill through that we used to take a look at the data, because we saw those two things as being very, very highly predictive in our visual analysis of the data. So let's just take a look and say, look, if we just built a model with just those two things, what kind of results would we get? Okay, so what I'm going to do here is I'm going to say, okay, great. We're going to create a specific training data frame, and I'm just going to call this random forest, or rf.train.1, for the first training data set for our RF data model exploratory modeling, excuse me. And what I'm going to do is I'm going to go, hey, grab me the first 891 rows out of the data combined data frame, because those are the ones with the labels. And then I'm going to say, hey, I only want 2 columns. I want the P class and I want the title. That's all I want, right? So this was a very minimal data frame just to explore modeling the problem space with just these 2 features. And then I'm also going to create a dedicated label variable. And in the data.combined data frame, we created a factor with 3 levels, survive, basically 1, 0, and none, because the data.combined has all of the data in it, including the training data, which has no labels. So, but to actually train a model, we just need essentially the training data set's version of the survived variable. So I'm just going to grab it directly because it doesn't have 3 factors, it has 2. You either lived or died. So I'm just going to grab that, convert it into as a factor, and then cram that into my random forest label variable. So now I've got my training data and my labels. Okay, next up, as we'll talk about in a second, random forests, not surprisingly, are random. So if you want to have some sort of reproducibility or some way to evaluate different runs of the random forest algorithm, setting the seed is really important, because otherwise you're going to get slightly different results every single time. That's by design. The way you counteract that is by using the set.seed, and as always, and this basically says, look, this is how you can set the state for the random number generator in R. So by setting it to 1, 2, 3, 4, classic example, we can get some reproducibility. Next up, we're going to call the random forest function. This is what actually trains an instance of a random forest for us. And using the parameters here, we can say, look, the x values, which corresponds to the training, we're going to point it at the data frame that we created. That's just our 2 variables of p class and title. The y's are the labels. Did you survive or not? And then we have our label variable for that. Now the last 2, you could in theory leave off, to be quite honest with you, when you're doing exploratory modeling, but I tend to set these just for the reasons I'm going to enumerate here. First of all, setting the importance to true tells the random forest algorithm, as you're training all of these decision trees that in aggregate make up the forest, hence the name, keep track of the relative importance of the features and the variables, so that way I can report out on them later on. And then lastly, this says how many individual trees are there in the forest. So by default, so we go back here, we can even see that in the help system. And where is ntree? Ntree is right here. So the default hyperparameter for random forest is 500 trees. And actually, to be honest with you, that is a reasonable default value, as we talked about before. I only up it to 1,000 just because, few extra trees aren't such a bad thing. So I tend to just do 1,000, but all 500 would work just as well. So you could potentially, in your exploratory modeling, just leave that parameter off, because you're not going to necessarily get a huge difference in the results. But I just tend to do 1,000. Okay, great. So let's train that. Nope. Actually, let's build our first, and then let's set the seed and train. And you can see here that was pretty fast. And the reason for that was we're only building 1,000 trees, and we only have 2 variables times 891 rows, so it's not a lot of data. So obviously, if your data set was huge, it would take a lot longer. Our data set's relatively small, so it was fast, which is exactly what we want for exploratory modeling. Okay. By default, the object that gets returned from the random forest function call, which I'm calling intuitively enough random forest 1, actually is set up that you can print it out by default. So all you have to do is just run that line of code, and what you get is some really useful output. Let's go ahead and take a look at that more in depth. So first it talks about, hey, how did you call the random forest? What's the number of trees? And this is the number of variables tried at each split. This is actually also a hyperparameter called mtry that you can tune, but for exploratory modeling, the idea is not to worry about it. And again, the way the algorithm is set up by default, it works pretty well, so you don't really need to mess with this. Now, what's below this is what's really super interesting, but let's start with this thing called OOB. Now, OOB stands for out of bag. And again, you'll learn more about this in the videos that I showed you that are available on YouTube, but at a high level, if you think about your training data as an Excel worksheet, as a table, as a matrix, the way the random forest algorithm works, first and foremost, is that it takes a random set of columns and rows out of your spreadsheet and does that iteratively. Every single time it trains a tree, basically, it does that. Now, what it also does is it says, look, I will also replace, what a statistician would say, this would be sampling with replacement. That is, look, I will draw, let's say, 891, I'll do 891 tries, oh, excuse me, I'll do 1,000 tries because I'm doing 1,000 trees, excuse me, and 1,000 times I'm going to randomly select a collection of rows and columns from the spreadsheet. But here's the thing, I'm okay with any single time that I build a tree, I may select the same rows and the same columns more than once. That's what statisticians would call random sampling with replacement. So what that means is that if you do that a bunch of times, the same rows and columns are going to get selected a huge number of times while you're training the entire forest. And what that means is that, by definition, a certain number of rows and columns will never get selected for any particular training of a tree. And then you can actually say, look, you know what? I can actually hold that out. It's outside of my bag, out of bag. And then I can use that and say, look, I can train this tree with the stuff that I did select, and the stuff that I didn't select, I can then use that to test how accurate it is. So that's one of the powers of the random forest, is that not only can it help you with feature selection, it can also give you an estimate of how accurate your model will be in general. Now, Leo Bryman, the gentleman who created the random forest, would tell you that this is very, very accurate. My experience is it varies. It's awesome for exploratory modeling. It's not necessarily the value I would use in an actual Kaggle competition, for example, to say, hey, look, I'm about ready to make a submission, and I think my Boob estimate of the error rate is going to match what I'm going to see in my Kaggle competition. I would use something that's called cross-validation instead. We'll talk about that in a later video, but this is good for our purposes. Now, what this says is, look, on average, I trained 1,000 trees, and for each tree, they're averaging about an error rate of about 20.76%. Or the way to think about that is we're getting nearly 80% accuracy just using two variables, which is pretty good, which matches our intuition from our data analysis. It says, look, these two things together are extremely predictive of whether you lived or died. Okay, next thing that's really super important in this output is the confusion matrix. And what this basically says is, look, hey, broken down by our labels, did you perish or did you survive on the Titanic? What were the results of this random forest all up? And what we can see here is something that's extremely important. So you can see here at the intersection of the matrix, and really doesn't matter the way you think about it. This could either be the true value and this is the predicted value, or vice versa. It doesn't really matter. So let's say this is the true value for the sake of discussion, and this is the predicted value. So what this says is, hey, our trained model predicted correctly 538 records perished when, in fact, they did perish. And we predicted that 11 people survived, or we predicted that 11 people perished when in fact they did survive. Okay, which gives us an error rate of around 2%. So this model is about 98% accurate in predicting correctly when people perish, which is pretty good. Now, that being said, we know that already that the data is skewed. Remember, we can do this very easy. We can double check that again by going to train, survived. And we knew already that it's biased already. So most people perished. So that's not a surprising result. Arguably, this current model is pretty good at pessimistic results. I'm really good at identifying when you perished. Reflexively, we could say, okay, good. How good are we at correctly predicting that somebody survived? So here we predicted that somebody survived when in fact they perished. Ooh, not so good. Right? We have a tendency to say, oh, we tend to be a little optimistic here, or a little pessimistic, because you can see here our accuracy rate's it's less than 50%. So we're really good at identifying people who did in fact perish when they did perish. We're not so good at identifying folks that survived predicting people survived when they actually did. Okay. Moving on, this line of code, this is where we can say, okay, cool. This is where we can do the a graphical representation of the random forest algorithm's feature selection. We just run this line of code and we should get a plot here. I'll just make that a little bit, let's just zoom in, that's better yet. Okay, so not super interesting when you only have 2 variables, but if you have more variables, what you can see is, I won't drain what these mean, you can look it up in the help system, but in general, if you have more variables, you'll see a long list of the variables on the y-axis here, and generally speaking, where their corresponding dot is, the farther to the right it is, the more important that variable is. So as we can see here, and as we expected from our data analyses, title is actually more important than p-class for determining whether you survived in this model. What this is saying is, look, if just these if building a model with just these 2 variables, title was way more predictive than p-class is in predicting survival. All right, moving on. As we did our analysis, we were able to throw out a bunch of the variables as in our first pass as not being particularly predictive. So that was things like tickets and cabins and where you embarked. We got rid of age and gender because we used title instead, because title is a single representation of both of those concepts combined. But one of the things we did identify that was potentially predictive was the SIBSPA, or the number of siblings and or spouses that you were traveling with. So let's go ahead and add that to the model. Let's train a new model and add that to the number of features that is. And we'll just call that 2. And the rest of the code is basically the same, so I won't drain it. Okay, let's take a look at that. So this is particularly interesting. With just the 2 variables, we got an error rate of 20.76%. But when we add a third one, we got more than a 1% increase in our accuracy. That is a 1% decrease in our error rate. That may not seem like much, but in machine learning competitions as well as business applications, often 1% improvement is huge, right? For example, the famous Netflix prize competition awarded $1 million to the first team that could increase the accuracy of, or improve the efficacy, I guess I should say, of the Netflix recommender by only 10%. It was worth $1 million. So 1% is huge. If you can add one variable and you get a 1% increase in your accuracy, 1% decrease in your error rate, that's huge. So this confirms our intuition that says, look, we thought SIBSPA was predictive, and sure enough, yes, it is. It helps out the overall model. Now, how does it help it out? It's kind of what we would expect, which is it dramatically increased our accuracy rate for those who survived. Now, reflexively, it had a negative impact on our accuracy for those that failed. But while this went up ostensibly 9%, you can see here around 9%, this decreased by almost 17%. So great, I'll take that trade-off any day of the week. Now, I have to caveat that with, that statement is bold, but it makes sense for the purposes of this application, which is overall accuracy is how the Kaggle competition for the Titanic survivors is judged. So we essentially give equal weighting to whether we make a incorrect prediction for those who perish versus an incorrect prediction for those who survived. They're equal. We don't really care. We'll mix and match that all day long as long as an aggregate we're the most accurate we can be. Now, there are many situations where that won't be true. For example, let's say for a fatal disease, a test that detects whether or not you have a fatal disease. A false positive telling somebody that they have the disease when in fact they don't is bad. It's not nearly as bad as a false negative, which says, no, we don't think you have the disease, even though you do. So that's, in that situation, you probably wouldn't weight errors exactly the same. So as you do your exploratory modeling, you would want to incorporate that into your analysis and understanding. But in our case here, it's very simple, which is good, which is they're equally fine. So we're willing to make that trade-off if our overall accuracy increases, which it has here. We got it by over a percentage. That's great. Okay, so we also thought that Parch was potentially predictive as well. So let's take a look here. Let's create a model and evaluate it. Instead of SIBSPA, let's use P-class, title, and Parch and see what happens. Okay. So this is interesting. So Parch is predictive because we improve over the original model here of 20.76% down to 19.98, but it's not nearly as predictive as SIBSPA, which is interesting. Okay, so we say, look, they both have predictive power, but one is better than the other. So inevitably, the next question is well, what if they're like chocolate and peanut butter? Are they better together? So we can go ahead and do another model that says, look, let's do P-class, title, SIBSPA, and Parch and see what our results are. And again, you'll notice that I'm using the same seed every time, so that way we can actually compare the models legitimately and say, okay, we know that the random seed is going to be the same, so the processing of the algorithm is going to start at exactly the same point every time, so that we can know that the only thing that varies between the results are the features that we're plugging in. Okay. Let's run that one. All right, sweet. So the combination of SIBSPA and Parch, which is what we would expect based on our analyses, is that the combination of them actually improves the model again. So for way of comparison, let's go ahead and pull up the first model. So we've gone a full 2 percentage points down in our error rate just by adding SIBSPA and Parch. And what that probably tells us intuitively is that, look, as we would expect, the number of siblings and the number of children and the number of parents probably matters, right? So we have this theory that of women and children first. So that this holds out with that. We also have the theory that wealthier folks tend to survive. That also holds out. And what also probably holds out too is they say, look, as we saw, maybe smaller families in second and third class had a tendency to survive better than larger families just because of the inertia of, let's say, being in the bowels of the ship and getting 5 children all the way up topside is probably, unfortunately, not likely. So this kind of reinforces that intuition here. Okay. Excellent. So we also said, hey, let's create a family size variable, which says, look, let's take this concept of for each individual record, we start with 1. I'm traveling with myself, so my family size is at least 1. And then I will add to it the SIBSPA and the Parch variable. So this is really this idea of saying, look, let's engineer a feature that says this is the total family size. Is that predictive? It's essentially marrying this idea of SIBSPA and Parch together. And sometimes that's helpful for an algorithm because sometimes algorithms can't necessarily intuit combinations of variables. So for example, our decision trees may say, look, if your SIBSPA is over 2 and your Parch is over 2, then go down this branch of the tree. But what it doesn't really understand is what's the total family size. The algorithm isn't that smart. So sometimes deliberately engineering a feature may be potentially helpful. So let's take a look at that. We thought it was predictive. Let's say, look, if I just say P-class, title, and family size, and the reason why we'll try this first is because implicitly, family size incorporates the idea of both Parch and SIBSPA. So you could make an argument that putting those two things in the model may potentially be redundant. So we'll just start with family size first, see what we get. And that's an interesting result. So our total error rate now is 18.41%. versus 18.52. It's a small improvement, but this is an interesting result. It it seems to validate, this exploratory modeling seems to validate our intuition that says, look, family size actually matters. And probably the random forest algorithm isn't necessarily very efficient at combining the idea of SIBSPA and Parch to arrive at this idea of aggregate family size. So we'll give it an explicit feature that says family size and see if it works. And the answer is, yeah, it works better. Not a lot better, but you know what? In the case of Kaggle, 0.1% sometimes can be the difference between a top 25 placement or a top 10% placement or the next bracket down. So it's nothing to sneeze at. And more importantly, this exploratory modeling gives us some ideas of where we may go for feature engineering, which says, look, family size matters. So the question may be to explore in the next video series potentially, or in the next video I should say, or the next video, or maybe one of the videos further down the line, is explicitly breaking this family size out, characterizing the family size in terms of the number of children, the number of adults, whether a wife is traveling with a husband or a husband traveling with a wife may be important, because it's saying, look, family size matters. It matters more in aggregate than just SIBSPA and Parch by itself. So that's really good. Okay, so, but because this is so quick and easy to do, it makes some sense to actually just explicitly try it. Like our intuition was, if we add SIBSPA, it's not going to really do much because family size already implicitly incorporates the knowledge, the information, the predictive power of SIBSPA in it already. So, but let's just try it. Doesn't hurt us to try it explicitly. And here we go. Okay, so let's break this down, right? So at the first level, this seems to be pretty indicative, right? If we add SIBSPA, our error rate goes up. And so that means our accuracy goes down. So SIBSPA, it seems to be confusing the issue. And we can see down in the confusion matrix how that breaks out, which is, okay, if we add SIBSPA, our error rate for those, for our parish predictions goes down a tad, but then our error rate for survival goes up disproportionately more, which then nets out to the fact that our overall error rate goes up, our accuracy goes down, which matches our intuition. But just, again, because this is so fast and it can't really hurt, let's go ahead and try that again with adding Parch to the mix. And as we saw before, Parch isn't nearly as predictive as, well, I shouldn't say nearly, that exaggerates the difference, but Parch isn't as predictive as SIBSPA is. So as we would expect, when we add SIBSPA to it, the error rate goes up even more. Right, and then here's the same. Now this is interesting that the error rate hasn't actually changed here. That's interesting, right? So the error rate between SIBSPA and Parch, when you have family size, doesn't really change much. What the problem is that we get worse at predicting survival, which is interesting, which may be indicative of the fact that family size is actually the thing that is predominantly used for determining whether or not you perish, which is the thing that didn't vary between these two. Because remember, setting the seed is trying very hard to reduce the variance between each run of the random forest algorithm so that we can say, okay, as we just alter the features that we use in training, that's going to be the primary source of variation between runs. So reflect, just thinking about it, the only thing that varies between this value and that value is whether it's SIBSPA or Parch. So we can say, look, and if these errors are the same, maybe that's indicative of, these error rates are exactly the same. Maybe this is indicative of family size being the disproportionately important variable for determining whether or not somebody perishes. And we can take a look at the plots just to verify that. I've been ignoring the plots here for a bit, but let's take a look at it. Okay, so here is our variable importance plot for the 7th random forest that we built, which has the features of title and p-class and family size and parch. And what we can see here, once again, is, man, title is way, way more important than anything else, which basically means that gender and your age is the single most important thing, which jives with this idea of women and children first. P-class is the next more important thing, which is our proxy for wealth. So that's important. Not nearly as important as women and children, but pretty important, which matches into our intuition. And family size is the next important thing, and it's, non-trivially more important than parch. We can go back and double check that and say, yep. Same thing holds for SIBSPA. Family size is more important. And we can see here in R5, this is our best single model in our exploratory session today in terms of accuracy, which I alluded to this last time in the third video, but I think it's worth mentioning again, is, this idea of Occam's razor, right? Generally speaking, we prefer simpler models rather than more complicated models. This is an example of that, which is, hey, look, you can actually get, if you have the right features, you don't necessarily need a lot of features to actually get a reasonably predictive model. This kind of shows that. And this was the next most accurate model, which is the combination of SIBSPA and parch, and so on and so forth. I won't drain all the rest of these plots. So we saw that RF5 was our most accurate model. So let's pull that up again. Okay, and so let's say, and just so that we can keep it easy, let's calculate what our accuracy rate is. Okay, so our accuracy rate, so the random forest is going to predict that in general our estimate of our accuracy is going to be around 81.5% with just 3 features, which is pretty cool. But for the sake of argument, let's go take a look at where that would place us in the general scheme of things in the Kaggle competition, just as a benchmark. Kaggle.com. Ooh, there's me. Yay. There we go. Titanic. Let's go to the leaderboard. And you did now. Okay, cool. Let's go ahead and maximize that. Now, first thing that we should note is that the Titanic competition is interesting for a couple of different reasons. One is it's very broadly participated in, right? This is basically an ongoing competition. It'll stop in, at some point, and they'll just restart it again. Lots of people do it. So these are teams. Most of the time they're individuals, but they could be teams of people competing under a single name. But a lot of folks competing. And the second thing is that this competition is ripe for cheating, because as you know from our data analyses, it's extremely unlikely that you could really build a model that gets you 100% accuracy, which is what all of these show, because there just doesn't seem to be enough signal in all of the variables to determine that. So, however, you can literally build a model that says, hey, look, I can actually go find all the names in the test set. I mean, we haven't actually looked at the raw. We did look at the raw data in video 1. The full names are listed there. I could go out on the internet and actually find everyone who lived or died by name and build a model that way. So, for example, I don't want to accuse anybody, but one submission with 100% accuracy, that seems a little fishy to me. Okay. And I would say a lot of these, are interesting. I mean, one submission at 99.5% accuracy. Yeah, I've competed in this competition myself, and I can attest that these things are fishy. So, realistically, we can scroll down, and when you start to see blocks of numbers being the same, that's pretty indicative of probably legitimate scoring. And the reason for that is that nowadays Kaggle allows for the posting of scripts to a particular competition. And what happens is that folks do a submission and they'll just post on the forums, "Hey, look, I just did a submission with this script, and it scores this amount." And all you have to do is you can go in there and you can literally tell Kaggle, "Hey, I want to submit the same script under my user account," and you'll get the same score. So you can see here, a bunch of 83s. That's probably indicative of this thing going on, because you've got a couple here that are just one. I've submitted one score and it's exactly the same, but then I've got people that have done 25. This is maybe indicative of a scenario where this person's been competing in competition and they've done a bunch of submissions and they found on the forum a script that somebody else implemented and they just submitted it and it's better than anything that they've done. Nothing wrong with that. It's all part of the learning process. And same here with the 82, 75s, and then, oh, here's a whole bunch of 82.297s. So yeah, okay. And then some 81 8s. So, wow, a lot of 81.8. Okay. So, which is good, because now we're saying, okay, look, if we take Dr. Leo Breiman at his word, and the OOB estimate of error rate is actually quite accurate. It's a very accurate estimate of how well we'll perform on unseen data. So this would be the test data in this case that we would submit to the Kaggle website. We should expect to get around 81.59. And if you assume that's accurate, 81.59 would put us, right around right here. So 213th place, which would be top 10% placement on our first submission, assuming, of course, that the estimate is accurate. It's not bad. Not bad at all. Top 10%, just three variables, pretty good. Just using a random forest algorithm, no tuning, not bad. So the reason why I bring this up is that I would argue that hopefully this illustrates the method to the madness now of why it's so important to do data analysis, why it's so important to do feature engineering, because it matters. It matters more than anything else. It matters more than what algorithms you use. It matters more than how you tune it. Those things are important, as I've said before, don't get me wrong, but they are immaterial. Feature engineering, understanding the data, is the number one thing. So with that, I will conclude. Hopefully you've enjoyed this video. Hopefully you're starting to see the big picture here, or maybe you already did, but you're just happy that I'm finally getting around to it. Either way, I look forward to the next video, and until then, happy data sleuthing.